Hi, I'm Paul Liu, and this is my project proposal, Understanding the Mechanical Reliability of Superhydrophobic Surfaces. There's a lot of interest in superhydrophobic surfaces, and they've been inspired by surfaces in nature on the lotus leaf. The lotus leaf consists of hierarchical structures at the microscale and nanoscale, and that's what helps them repel water, like you see here on the surface of the leaf. As water droplets fall on the leaf, uh, the droplets roll off, taking any dirt or particulates with them, and that allows the leaf to perform photosynthesis. A lot of synthetic surfaces have been created, as you can see here in the bottom left, with plastics, as well as glass. And superhydrophobic surfaces have been demonstrated to create a lot of unique functionalities, things such as self-cleaning, anti-icing, stain resistance, and even antimicrobial surfaces. So this is a normal glass. You can see that it doesn't repel liquids so well. The liquids are wetting on glass. But with nanostructured glass, you can see that it repels a wide variety of liquids, including coffee, various oils, blood, and so on. Under a scanning electron microscope image, this is what the glass looks like, and it consists of very tiny nanoscale structures that provide for superhydrophobicity. By minimizing the amount of contact area between the water droplets or liquid droplets and the surface, then you can create surfaces that are very repelling towards liquids and easily roll off. And this is what creates your superhydrophobic surface. This is a more zoomed in image, and you can see what it looks like. By really creating very small contact area between the liquid droplet and the surface, you have mainly air contacting the liquid droplet, and air is very strongly repelling towards the droplet. However, one of the challenges with creating these superhydrophobic surfaces is that you now have very small contact area between the droplet and the surface. And because you have such small contact area, when there are forces abrading on the surface, then you have very high mechanical stresses, and a lot of these types of structures can be easily removed. So reliability is a key challenge. So this project seeks to realize combining fabrication, characterization, and machine learning techniques to characterize how superhydrophobic surfaces degrade under mechanical abrasion. The first task is through macro scale abrasion characterization. So this is doing tests such as linear and rotary abrasion, looking how the wetting properties change, looking at the static contact angle, as well as the contact angle hysteresis, and characterizing various properties and how they change with abrasion. So how much mass is lost, how do the optical properties change, how does it look, what does the structure look like under a microscope. We also want to characterize these surfaces with nano indentation and nano scratching, and we can also do in situ scanning probe microscopy imaging. So as this probe is scratching the surface, we can actually in real time see how material is being removed. Through this characterization, we can understand the Young's modulus, the hardness of the surface, the scratch resistance, and how surfaces can delaminate, as well as various friction coefficients. We want to combine this data with Bayesian learning so that we can optimize properties such as high contact angle after abrasion. And we additionally want to adapt some of the image characterization methods to better understand how the surface morphology is changing. So the deliverables from this project are data sets from microscopy, as well as various macro scale abrasion, nano indentation, and nano scratching experiments. And we also want to provide for mechanistic insight into how to make superhydrophobic surfaces that have some of these remarkable properties more mechanically reliable with regard to abrasion.